In section 10.2, you're going to go over 3 by 3 systems of equations. That's going to change the geometry considerably. Now, back when you're doing 2 by 2 systems of equations, it worked out pretty nice. You could have one solution when 2 lines crossed, no solutions, or an infinite number of solutions. So 1, 0, or infinitely many solutions. The same thing is going to be true in the 3 by 3 case. It's just that the geometry gets a lot more involved. Instead of dealing with lines, you're dealing with planes. So if you're in a room someplace, imagine the front wall, the right wall, and the ceiling. All 3 of those planes meet together in the corner, that corner point. And that's what you want to have happen with your 3 planes. When you're dealing with a system of 3 by 3 equations, that is 3 equations and 3 unknowns, these are no longer just lines, they're planes. Now, for this one, we want to make sure, or we want to try and solve the system of equations. For myself, out of my convenience, I'd probably reorder these things first. I'd probably go x minus 7y minus z equals negative 6, and then negative x plus y plus 7z equals 0, and finally 5x plus y plus z equals 6. Just out of my convenience, just letting you know you can do that if you want. But the idea is to take one of these equations and use it to eliminate a variable from the other 2. So look for something that has a coefficient of 1 or negative 1. It'd be easy to use the first equation and get rid of the z's from the next 2. I use the first equation to get rid of the x's from the next 2. So all you need to do is add the first and second equation to get rid of the x there. So that gave us one equation. And then negative 5 times this equation added to this one gives us a second equation. Now notice both of these equations just depend on y and z. So you can solve this system of equations any way you like. Now personally, I would suggest you solve this by the addition method, maybe multiply by negative 1 times this equation. So negative 1 times that equation gives me this. Add it to that equation, and I get a nice easy equation for y. What does y equal for us in this case? Y equals 1. And if y equals 1, then I can plug that value of y back into one of these equations, say here. So I get negative 6 plus 6z equals negative 6. If I add 6 to both sides, I get 6z equals 0, which means z equals 0. So I've got 2 of my solutions here. Z equals 0 and y equals 1. With those 2 values, I can come in and solve for x. I'll go back to one of my original equations and plug in z equals 0 and y equals 1 and solve for x. Add 7 to both sides. I get x equals 1. Now as far as your solution in WebAssign is concerned, it's going to be 1, 1, and 0. That's the nice case. That's what you'd like to see happen when you're working with your systems of equations. It's not always going to happen. Let me show you a couple other things that can happen. So let's see here. Yeah, let's take a look at this one. Now this one, you can make your life a little bit easier. If you notice, this middle equation is missing a y. So the clever thing to do would be to get rid of the y from this equation. That way you don't have to do as much work as you did in the first one. In the first one, I had to use that trick twice. I used this equation to get rid of the x here and here. So I had to do that twice. If you get rid of the y, then you only have to do that once. And you'll end up with 2 equations that just depend on x and z. So if I add these 2 equations together, row 1 and row 3, I end up with 3x minus 6z equals 11. So that gives me my two equations. I've got one right here and one right here. So let's put those two together. You can solve that two by two system equations any way you want. And for my case, I'm going to multiply by -3. That gives me this. And when I add these together, I end up with 0 equals 11. Well, I know that's not true, so this is inconsistent. I believe Web of Science is just going to ask you to put in no solution. All right. Hopefully you see that this actually is less work than our previous one because we didn't have to get rid of the y variable from that second equation. Now there's one last thing that can happen, and I'm going to show you two examples of that because it's kind of difficult. So again, let's look back at a system of equations. I'm going to pick the first row and use that to eliminate a variable from the next two. Now I could eliminate the z's, I can eliminate the y's, I can eliminate the x's. I chose to eliminate the x's. So you multiply the top one by -1, add it to the second one, and I get this. I do likewise, I multiply this by -2. -2 times row 1 added to row 3. Let's see. And -2 times that would be -2x minus 2y plus 2z equals 0. And when I add, well, wait a minute. If you notice, when I add, I get the same thing both times. And if that happens to you, you know, when you go to solve for your system equations, y minus 2z equals -5, y minus 2z equals -5. If I was going to try and solve this by the addition method, I could multiply everything by -1, and I see I get 0 equals 0. That's telling you that your system of equations is dependent. So you can kind of stop here and do this. I'm going to take and solve for y. That just means moving the 2z to the other side where it becomes positive. And now I've got an expression for y. And I'll use that expression for y in a minute. To get an expression for x, I can take this expression and plug it in here. Right there. So 2z minus 5. Combine like terms. 2z minus z is z. So I end up with x plus z minus 5 equals 0. If I move all this stuff to the right-hand side, I get -z plus 5. So that's my solution for x. That's going to go here. I had a solution for y. That's going to go here. So overall, it's going to look like -z plus 5 and 2z minus 5. Now, I don't know what z is, so I'll just leave it as z. Be careful. Sometimes they ask you to put this in the form of a t. So it'll be, instead of -z plus 5 and all this stuff, it'd just be written with a t. -t plus 5, 2t minus 5, and t. So that'd be writing it in the form with a t. Now there's another little bit trickier version of that that you're going to likely run into. And kind of again, just to remind you that the order in which you write these doesn't matter. I switched the order of this system of equations just to put this on the bottom. I wanted something with a coefficient of 1 up top. And I apologize that I keep on getting rid of the x's. You could get rid of the y's very easily. That'd be no problem. But I'm going to use this equation to get rid of the x's here and here. And I did that in this first equation, and I got really lucky because I actually figured out what z was. Because the y's and the x's canceled, leaving me with z equals 1. And then I repeated that for this one without really thinking, and guess what happens? -9, z equals -9, so z equals 1 again. Duh, I should have expected that one. Sean, I hope you're catching this. This one's inspired by you. All right, so z is 1. I know that. Let me put that z equal 1 up into the first equation, like this. So that's 4 times 1 gives me a 4. So if I, let's see, I can subtract 2 from both sides, or subtract 4 from both sides. That would give me, yeah, that would give me a -2 there. There's my Photoshop. There we go. If I move the 2y to the other side, it's going to become negative. If I subtract 4 from both sides, that would also be a negative. So that tells me x is 2y minus 2, or minus 2y minus 2. Y is whatever, and z was 1. So that's how I can write my solution in this particular case. So it's all depending on the value of y. If they're asking for it in terms of t, I'll let y equal t. This is still a 1. That'd be -2t minus 2.
Why couldn't you find y the same way you found x?
Well, at one point or another, you're not going to be able to solve for all the variables. So at some point, you're going to have either y in terms of x or x in terms of y. So yeah, we could have solved for y here. I could have. That's a good question. So let me go back to this equation right here, and instead of solving for x, I'll solve for y. So that would give me, let's see, I'll still subtract, this time I'll subtract x from both sides and subtract 4, so I'll get 2y equals negative x minus 2. And then if I divide both sides by 2, I end up with -1/2 x minus 1. So, okay. Now I can write things in terms of x. X can be whatever, and y is -1/2 x minus 1, and z is still 1. So that would be a different form of the same answer.
Why can't you put both x and y answers, or do you have to leave one variable out?
Well, because you want to write it as a function of one variable. That way, when you change this, you also get this.
Oh, okay.
All right, so that way it traces out a line. It's a parametric equation for a line. Now, I think I still have up something that I did for us in the last section here. Let me see if I can't find that one. And that was this. So here's a 2x2 example of the same thing. But when I have points in this form, you know, one variable and then something of another variable, that traces out a line. So when I change the value of s, I'm getting all the different values or all the different points on this line. And you can see that when I click this, there's my line. And for different values of s, I can find myself anywhere on this line. And so by keeping everything in one variable, I allow myself to trace out a line. It's just that that line is now in 3 dimensions, and we can't really see it very easily. So that's why, you know, the short answer is that's why you're just putting it as a function of one variable. Now again, if it was in terms of just the one variable, like t, there it is, okay? But these would be equivalent. They would give you an equivalent set of points. So, cool, good question. Anything else? Did that answer things for you?
Yeah, makes sense.
All right, good deal. Okay, go get them.